Good morning, everyone. Welcome to the class. This class will be lecture 2. Still, I'm going to give you the overview of the class in this semester. Especially today, I'm going to talk about digital transformation, computing, and interconnections. I'd like to give you the basic concepts of digital transformation and increasing computing performance. We have strong pressure to improve computing capabilities. And then, in order to provide enough computing capabilities, you have to have good interconnection designs. So our class in this semester will be to talk about the basic principles of interconnection designs. There are many different ways to explain digital transformations. I usually explain the digital transformations using the concepts of platform X structure. Here, X means many different applications. So I would say platform X is another phase of digital transformation. We have pyramid here. This is my own concept to explain the platform X structure. Actually, this platform X is a structure to enable digital transformation. There are many companies who has this platform X structures. For example, Apple, Tesla, Google, and Microsoft. These companies are leading companies in the stock market, and they are rated very highly in IT business. These companies, Apple, Tesla, Google, and Microsoft, has in semiconductor design capabilities because semiconductor will determine the computing performance and artificial intelligence capabilities. Then they have computer business or automotive vehicle business or smartphone business. All these three can be regarded as computer. On the top of that, they usually have data centers to store big data for AI training. Also, they have many different services such as AI and metaverse. They need to have big computing data centers. We usually call it as data center. And these computers and automatic vehicles and smartphones are used to collect big data to train artificial intelligence. So on the top of data center, they have to have the capability of AI. Also, they have to collect big amount of data using their computer system, and those data are stored in data centers. This big data will be used to train artificial intelligence. Artificial intelligence will be a weapon to concentrate their customers and to be dominant on the market. On the top of AI, you will have content. Contents will be a form of movies or documents or YouTube. There might be many different games, or there could be many different contents. On the top of contents, they may provide some services. Service can be education, medical healthcare, culture, logistics, production, finance, insurance, and advertisement. So actually, they will obtain huge amount of profit at the service level or content level. But in order to have to be able to dominant in this market service and contents market, they need to have AI. In order to train AI, they need to have big data. But anyway, during the inference and backpropagation, and they need strong computer capabilities. And this computer capability will be determine their performance of semiconductor chips. That's why Apple has a service and contents as well as AI, data center, computer, and IC all together. But this semiconductor and computer and even data center, this performance of these three basic blocks will be heavily depending on the interconnection design of data center, computer, automobile vehicle, smartphone, and semiconductors. So the major focus of our class in this semester is to talk about interconnection design principles at the level of data center, computer, and IC. The purpose of this performance improvement is to provide enough computational capability for artificial intelligence training and inference. Those are the target of classes in this semester. So these platform X companies will be dominant in the market, and I expect them to grow in the future. If you have a little bit of cash available for the future, you can invest your money for the stock of these companies. Maybe less than $1,000, no more than that. This graph shows the Apple stock price over the last 5 years. It was continuously increasing for the last 5 years, and I expect them to grow more and more because Apple has very good, strong platform X structures by themselves. I have been at KAIST for more than 30 years, and I graduated more than 100 PhD and master course students, and about 9 of them are now working in Apple. Apple are hiring them because they want to improve the quality of performance of their data center, smartphone, and semiconductors. Many of my former students are now working at Samsung, Tesla, Google, and Microsoft. And the reason they are hiring my former students are high quality services and contents. The most important part of this pyramid platform X structure is artificial intelligence. And I'd like to talk a little bit more about AI. There are some benefits of AI. They will work for us for spiritual works, and they can help us to save time, labor, resources, capital, and energy. So if you want to be very competitive in time, labor, resources, and capital and energy, you should use artificial intelligence. It may be true for companies. For us individuals, it will give us time for more creative activities. And we do not need to work. But that's good. So we may be improve of our quality of lives. But in the worst case of AI is that if sometimes we want to work, but we may not have chance to work. That could be a social problem in the future. Anyway, in order to train AI, as you know, we need big data. Big data is a way to teach artificial intelligence, especially for supervised learning, such as CNN and LSTM and GPT-3. So if we have more amount of data, we may have more clever and accurate artificial intelligence. This is a conceptual figure to show the increase of generated big data with a different time of period from 1980 to 2040. In middle of 1980, we start to use personal computers. I may assume that many of my students right now were born after this, but when I was a college student, I start to use personal computers. At the time, IBM XT, AT were most powerful computers. I love to use them. Also, when I was a college student, I start to use 8-bit Apple computers. That is the start of personal computer era in the history. At the time, I used the basic programs to do some computations and graphics work, and that means I generated some data. In the early 1980s, internet is introduced and I start to use Netscape. Right now I'm using Chrome, but at the same time, Netscape was the first internet service. And internet is creating a lot of new data. In 2000, we start to use the smartphone and Google smartphone or Apple smartphone. And by using that, we start, and also its smartphone had camera. So we generated a lot of new data. Recently, I think YouTube is a big momentum to generate more visual data. Visual data has more bit amount than the pictures or images. Now we are at the beginning of 2020. I think because of Corona, a lot of business and lectures and activities are going on online. That means we are generating more and more visual data. And also we are seeing 3D cyber data being called as metaverse. I think this online business and metaverse, it will be a strong driving force to increase the amount of data. And the middle of 2030 or 2040, I assume that we were gonna have more bio and healthcare data. Our DNA and each cell data may be stored by somebody, and then may be very useful to increase our life and qualities. So I think the amount of data per year may be more than 10 to 24 bytes. That is the really big amount of data. I'm sure this increasing amount of big data will be very useful for training artificial intelligence. But now, I would like to emphasize at this moment is that previously, from PC to YouTube era, most of this data was generated by human beings. You took pictures or YouTubes and uploaded to the YouTube. But from metaverse era, computer itself will generate the three-dimensional data for human or AI educations. So our data generation will be more depending on the performance of metaverse. And metaverse is actually a 3D cyber world generated by computers. And computer performance will be heavily depending on interconnections. And that's why our class is becoming more important. So originally, Platform X started in the PC period, but now we are on smartphone period. More data is generated on the smartphone, and AI application will be shown up on the smartphone. But sooner or later, I think automotive vehicle will be a major platform to obtain the large amount of data and to apply the artificial intelligence. And sooner or later, we're gonna live in metaverse period, then most of data will be generated in the cyber world, and we're gonna live in the cyber world, and this cyber human being will be more working than actual human being. I call it as artificial humans. So this is summary of metaverse. The purpose of metaverse is first to transit digital transform to cyber world. In cyber world, we don't need to have PC or smartphone or automated vehicles. You just put on your head mount display and live on that. Second purpose of metaverse is that we don't need to physical layers. We don't have to. We just sit in on a chair and put your head mount on your face. Also, metaverse will provide unlimited data generation for machine learning training. Unlimited data generation will be done by computers. So we will be more depending on computing and computing. And also by using the metaverse, it will create a cyber world for human economic activities. So more and more profit will be given to companies who has metaverse. So once again, in digital transformation era, most important technology, I believe, is artificial intelligence. There are three technology enablers for artificial intelligence. First one is deep learning algorithm. Deep learning algorithm is basically matrix calculation and for the propagation and backward propagation. I would say 90% of this calculation of machine learning and deep learning is matrix calculations with some memories and nonlinear functions. For teach artificial intelligence, we need big data. I was just talking about this in the previous slide. As I told you that in these days, big data will be generated by computers. Another technology enablers for artificial intelligence is improved computer performance. Because this deep learning algorithm is very computational intensive, and big data is generated by computers. So especially in metaverse, computer is doing almost everything. So I think computing the group or person, group or company who has strong computing power will control these digital transformations. That's how Amazon, Google, Apple are spending a lot of money, Microsoft is a lot of money to build up their data center, who has the huge amount of servers in a location. So if you want to be dominant in the business in digital transformation era, you have to have very strong computing power. Typically, this computing power will be depending on three factors: performance of GPU, performance of DRAM, and interconnections. As a conclusion, I would say improved computing performance will be heavily depending on interconnection design. That's why I'm opening this class in this semester, and I'm going to talk about design principles of interconnections. Let's look a little bit more about interconnection, the artificial intelligence. This slide shows the basic simplified structure of machine learning and deep learning. It has input layer, hidden layer, and output layer. Each cell represents a synapses. It has memory element. The input layer digital data will be submitted or transmitted to hidden layer by this arrow by numerical multiplications. At certain synapses node, if the amount of summation of this arrow goes over the threshold, it will be transmitted to next level. Let's take a look at this perceptron. So this is input vector represented by x1 to xn, and we have weight w1 to wn. These are multiplied and summed at this node, and if we're gonna apply this summation to a nonlinear function that is being called as activation function. Usually it is a form of logarithm nonlinear function. There are many different ways to making this nonlinear function. But anyway, this input vector will be multiplied by this weight, and that can be represented by a matrix multiplications. During the training process of this perceptron, we're gonna determine W0 to Wn. In this figure, we are showing you just one perceptron, but actual deep neural network may have billions of billions perceptron. And in a microsecond or nanosecond, we have to complete this training. That means we need to have a huge amount of parallel computing capabilities. That's why we are using multi-core structures such as TPU and GPU. As I told you before, during the inference and backpropagation process of artificial intelligence, we're gonna have many matrix calculations. So when we are doing the matrix calculation, we have to calculate the Cij. That means we have to multiply A and B, and we have to summarize that. That means we have to bring this A and B data from the memory, and we have to calculate the summation, and we have to store it back to the memory. Another meaning of this matrix calculation is that Cij and C11, C12, and there might be hundreds or billions of these Cij, and they can be calculated in parallel, because Cij and Cij, different Cij is not depending on each other. They can separately calculated in parallel. That means your computing capability has to have parallel computing. At the same time, you're gonna have many operations to bring this data from your memory, and you have to calculate it, and you have to store them again. Billions of billions, this operation has to be executed in a second. That is the computing architecture should provide for your artificial intelligence calculations. But unfortunately, we are using the von Neumann computing architecture. What does that mean? Our CPU or GPU and memory are physically separated. There might be traditional reason for that, because traditionally we made memory from magnetic tape, CD-ROM, floppy disk. Now we are using DRAM. CPU has started from transistors or vacuum tube. Right now they are in a form of integrated circuit. And the process of CPU, GPU, and memories are different. Memory are usually made by Samsung and SK Hynix and Micron, and CPUs are made by Qualcomm, Intel, AMD, and NVIDIA, and Apple. So these two companies are different. But in order to make those matrix calculations, we have to fetch the data, and we have to decode, we have to execute the calculation, and we have to store back to the memory. So billions of billions time in a second, we have to do this operation for this matrix calculation, which are needed for AI training processes. But what we found right now is that the CPU and memories are developed using the Moore's law up to now, and they are very fast and power efficient. Majority of time delay and power consumption occurs at number 1 fetch process and number 5 store process. Number 1 fetch process will be depending on your interconnection, and number 5 will be depending on interconnections. So in conclusion, I would say, in summary, I would say performance of your computing during the AI training and backpropagation will be depending on your interconnections. This is another study done by a group saying that in terms of power consumption, majority of power consumption occurs from DRAM to calculation unit. So as I said that before, number 1 and number 5, interconnection between memory and processing unit will determine the speed of your computation as well as the power. I would say, in this graphic way, I would say that right now in technological, we are now have technological challenges in data centers and computers, saying that we have big data, but we do not have enough technology of big data per second. So big data per second will be totally depending on how you design interconnections. That will be the focus of our class in this semester. The conclusion of part of lecture right now and partial lecture conclusion of my lecture right now is that AI computer has challenges because it has huge latency. It asks more bandwidth between the memory and the GPU. It asks less power consumption. At the same time, we want to have computers with mobility. Mobility means it has to be able to operate with battery power. I think these are the strong pressure of computer design as well as in semiconductor design. Once again, I would like to say it will be very strongly depending on interconnection design. Traditionally, GPU and DRAM performance was steadily improved because of Moore's law. But however, let's assume that in 10 years, we are reaching 1 nanometer scale. In 1 nano means we have 4 silicon atoms. So between source and drain under the gate, we have just 4 silicon atoms. So it is not going to be electronics. It's going to become quantum electronics. So it is hard to apply the circuit theory to describe behavior of semiconductor devices. And the more likely the device will behave as a quantum mechanical behavior. So I assume that we will have a more likely step function type because of quantum level of this current through this source and drain. And in order to see this kind of quantumic effect, probably we have to cool down these devices nearly up to the 1 Kelvin. So then the silicon industry will be totally different, and our design and all the theories of semiconductor device will be different. So what I'm saying is that we are nearer of Moore's law. So only way to improve the computing performance will be the interconnection design. So this is my expectation of future computing. We're gonna have more parallel interconnections between processor and memory. Right now, conventional graphic DRAM may have 32 or 32 IOs between processor and memory. And HBM, that is very advanced semiconductor solutions for AI computers, they usually have 1024 IOs. But in the long future, I would say millions and millions interconnections should be placed between GPU and memory. That means lines will be placed very close to each other, and we're gonna have very strong crosstalk issues and so on. And to enable this millions of interconnection between two different devices, I strongly believe that computer will be a three-dimensional structures. We need to have very innovative power and thermal control, because some devices, AI devices in 3D structures will have more than kilowatt from megawatt. It's a huge amount of power consumption will occur. So temperature will be very, very high. It could be almost a melting temperature of silicon and copper. So we need to have very innovative thermal solutions. Also, we are having very limit caused by von Neumann architectures. Probably we need to have new computing architectures. And in order to have this innovative power and thermal control and computing new architectures, probably we may need new materials. It may take very long time. To bring GPU and memory as close as possible, maybe we may need a same wafer or to make both processes. Then we may need different materials and processes. And at the same time, the solution should be cost effective. Otherwise, it will be very difficult to apply to us. I think these are the main direction of high performance computing system. So in order to provide very highly three-dimensional interconnections and very high speed, like 100 gigabps like that, we will have some design issues of interconnection. And I would say that is 5 methodologies that will be the class target of our class. Number 1 is signal integrity, how to deliver very clean digital signal from a chip to chip or inside chip. In order to send very clean digital signal, we have to meet the assumption saying that we have constant voltage and zero ground voltage. That may be described as a word saying power integrity. If you do not have good quality signal integrity and power integrity, it will generate electromagnetic waves, and it will interfere with adjacent circuits or devices or RF circuit or radio circuits. Especially for mobile systems such as smartphone and automotive vehicle, it will determine the reliability of and safety of your system. Especially in the case of automotive vehicles, if this electromagnetic interference can cause some malfunction of your sensors or processors, and it could make some wrong operation of your car, and it can create some accident. It is very dangerous to human and traffic. And also we're gonna have some thermal integrity issues, because you have to cool down. If you do not have proper thermal solution, your computer will not work. And even though this is not gonna be the major focus of our class, for design of these 5 I's, our group is working on to apply artificial intelligence techniques. This the first part of my class today, and now I will move on to next subject a little bit. As I mentioned before, so future interconnection will be the three-dimensional. So for example, on the top of GPU, memory will be placed on the top and another memory will be on the top. And then usually the thickness of this wafer will be less than 20 or 30 micron, so very thin. Then to make a connection between a chip to chip, the length of this interconnection will be very short. So because of that we're gonna have very small RC delays. And also, because of short distance, it will have less inductance. So it will be much better to match the 50 ohm impedance of your signal line. And when this VR is being used for power delivery, it will have much less inductance. That means we're gonna have smaller simultaneous switching noise. And another important feature is that because the diameter of this VR will be less than a micron in the future, that means we can put these millions of VR. That means we can increase the number of interconnection between a chip to chip. Then we can increase the I/O bandwidth between a chip to chip. Also, we can reduce the inductance of power supply. That means we can reduce the simultaneous switching noise. So I strongly believe that three-dimensional semiconductor structure will be the solution for data centers and servers of artificial intelligence. Once again, we also need to have a cooling solution as well. Our group, my students have been working together with me for last 10 years to design the interconnections for these three-dimensional semiconductor systems for artificial intelligence. One of the products which we have been working with local memory companies and US GPU companies, we was by working together, we was able to introduce this new HBM module. HBM is now on the market, and I think this is very expensive computing solutions for AI servers and metaverse and imaging process. But if you want to provide very high quality AI computing solutions, I strongly believe that you have to use this HBM system. In this case, DRAM is stacked on the top of each other, and the DRAM signal is going through silicon via, and it is connected to GPU. And the amount of interconnection between HBM and GPU was more than 1024. And because there are so many lines between processor and memory, we are using the silicon interposer, usually rather than PCB type of interconnections. So truly in the future, this HBM module will be placed on the top of processor in the future GPU. But we do not have enough good amount of cooling solution right now. This 2.5 structure will move on and go on for long time. And by having very specific vertical interconnection structures, we was able to demonstrate the measurement of more than 30 gigabps. I strongly believe that if we develop more and study more and more, we are able to transmit 100 gigabps through this through silicon via. Please assume that we're gonna have millions of this via, and then we can transmit 100 terabytes per second in a second between GPU and memory. That will be the strong requirement of next generation giant AI model or foundation AI model. Also, we was able to transmit more than 30 gigabps data through the silicon interposer. At the same time, in order to increase the I/O data bandwidth between GPU and memory, right now we are using 2-level digital system, but in the near future, we're gonna use the 4-level digital system to send 4-bit signal in a channel, because we are limited by number of channel. So this is being called as PAM4. In this semester, we're gonna talk a little bit about this architecture as well. Surprisingly, as I predicted before, or I suggest before right now, NAND flash, this is 32-story NAND flash, stack NAND flash memory. I think in the near future, it's gonna be 124 layers, stack 3-dimensional NAND flash will be on the market. If we stack this wafer on the top of each other, then we can easily make a 1024-story stack, vertical stack of NAND flash memory. Right now, this is SK Hynix 16 stack DRAM, and technically, I believe that they can put 100 of them on the top of each other. So even though this is very strong, very expensive solutions, I think we're gonna go to this 3-dimensional directions of future computing architectures. As I mentioned before, when we are making these 3-dimensional structures, our interconnection will be more likely vertical interconnections. Then we have to be able to properly design this bump and via and bump and via. And we have to design those interconnections. And next week, I'm going to give you the theory of transmission line structures. And this has to become 50-ohm transmission line structures. And those are some challenges to meet the requirement of semiconductor process. Our group is also doing some researches to put some active circuit at the silicon substrate and interposer. In the conventional package, the silicon interposer is just interconnection, but we're gonna put some commands such as power supply circuit or clock delivery circuit or PLL could be placed on the silicon interposer. So as I mentioned before, major direction of computing system will be the 3-dimensional system, and devices and interposers will be stacked on the top of each other. Why to do that? We do that because we want to maximize the interconnection, number of interconnections, and we want to minimize the distance, length of interconnections to reduce the latency of computation during the AI training and backpropagation. And also we want to minimize the power consumption and simultaneous switching noise. But one challenge to realize that 3-dimensional structure is that the temperature, power consumption of device will be huge, and the temperature will be huge, and probably we have to have water type of cooling solution, or we can use liquid water cooling solution or liquid nitrogen cooling solution, or your whole computer system could be immersed into the tank of liquid nitrogen or liquid helium. So temperature control will be the very important part of our semiconductor design as well in the future. Another big direction, which physically it will be 3-dimensional, but for a while, because of the, until we have very good thermal cooling solutions, we're gonna have 2.5D solution, in which case I would suggest heterogeneous computing. You're gonna hear more and more this word in the future in your careers. Here, we're gonna use the 12-inch whole wafer is becoming package substrate. It will provide the interconnections. On the top of that, we're gonna have CPU and GPU, HBM memory, and DDR memory will be placed on there, or FPGA, because CPU, GPU, and FPGA has certain advantages, and we will combine them together. And HBM has some certain advantage of memory, and usually for CPU, we need DDR type of memory. So we may combine all this device will be stacked on the silicon 12-inch wafers, then this 12-inch wafer will work as a supercomputer. Right now, majority of market for memory is the smartphone and mobile devices, and gradually, memory market or CPU, GPU market will be moved on to this. I believe Intel and NVIDIA will be competing or fighting a lot on this area in the near future. But surprisingly, always they need memory. HBM and DDR will be the memory, so SK Hynix and Samsung will compete on this market. And who is gonna make these packages? So a lot of companies will be working together collaboratively, or one company will be dominant and they will buy the other company. So I strongly believe this will be the solutions, and our students will work on this area for more than 30 years, next 30 years, and please look at these opportunities. Another solution which is being considered by US companies are quantum computings. Because silicon type of GPU and DRAM and interconnections are consuming a lot of powers, and it takes a lot of latencies. So some innovative scientists are now working to use quantum computers to replace silicon type of computers. But what I believe is that, this is my own belief, that quantum computer will not replace silicon computer. Quantum computer will work on certain areas, like, I don't know, some mathematical computations. It will take long time, maybe not forever. Quantum computer will not replace the silicon type of CMOS type of digital computers, because mathematics, logics, and infrastructures are totally different. And quantum computer has certain advantages of low power computing, but I was saying it may be very good for certain cryptographic communications or ARM computing or some area. But one disadvantage of quantum computing is that we have to cool down this whole computer up to 0.015 K, very, very low temperature. So it takes huge amount of instrument. I think that is the first problem. Second problem is that this is very secret. I haven't told them yet. Even though they are calculating this calculation very fast at this computational module, they have to go out. That means there is a long interconnections. So they have a much more severe interconnection problem because of the length of the system. As I told you that in order to reduce the latency and power consumption, we have to reduce the length. But because of these cooling structures, they are not able to reduce it very small size, like 100 micron or millimeter. They have interconnection, all the EMI, signal integrity, and power integrity problem. Second problem is that they do not have memory. They have very good computing capabilities, but memories are placed on the outside. The interconnection length between computing element and memories are very, very far away. That is against my law. That's why quantum computing is good some areas, probably, but not good for AI training and backpropagation. In summary, I would say that quantum computing is suitable for certain special computing, mathematical calculation, and encryption. But disadvantage is on the fact that it asks low temperature maintenance and how to make a parallel computing. As I told you that during the AI computation, we need to have parallel computing, but this is not suitable for parallel computing. It has very long interconnection length, and they do not have memory, so they have to have external memory. So this is the so once again, I would like to saying that now this is summary of my class, the first part of my class right now. We are living in digital transformation era. Most important part of digital transformation is artificial intelligence. In order to have very efficient and fast artificial intelligence solutions in your digital platform, you need to have a good computational capabilities. And unfortunately, GPU and memory are physically separated, and we have all the interconnection problems. So in summary, digital transformation will be heavily depending on the quality of your interconnection. And here is the summary: long interconnection delay and latency issues. So we have to design the transmission line to minimize these issues. If you design your interconnection in a form of transmission line, you can send data with the speed of light. And then also we have to increase the number of interconnection. We have to have millions of transmission line between source and receiver. But this is only the signal integrity concern. Also, we have power integrity concern. I would say the difficulty of signal design, let's assume that is 10. Power integrity design, the level of difficulty is about 3 times 30. And the ground design is much more difficult. And that is, I would say, the level 100. And again, you may have all these issues. And final solution is the shielding method, very cost-effective solution. And we're gonna talk a lot at this class. 오늘 여러분들이 많은 얼굴을 보여주셔가지고 박동열 씨 계시죠? 지금 아침 일찍부터 들어오셨던데 지금 계시죠? 마이크 킬 수 있나요?
예, 지금 듣고 있습니다.
출석부에는 없는데 청강하시는 건가요?
신청했는데 제가 한 번 더 확인해 보겠습니다.
그러시군요. 어제 자기소개 하셨나요?
어제 월요일 날 그 연결하기가 어려서 마이크는 자기소개 하진 못했습니다.
한번 자기소개 간단히 해주실래요? 어느 교수님, 어느 연구하시는지, 그리고 어떤 목적으로 수업을 들으시는지.
예, 저 그 안승윤 교수님 연구실에서 현재 박사과정 재학 중에 있는 박동률이라고 합니다.
네.
연구는 그 과제에 따라 하느라 좀 특이하게도 그 통신 관련된 그런 기법들, 그리고 최근에는 통신에서 발생하는 EMF 문제 관련돼서 좀 하고 있으며, 앞으로는 좀 인터커넥션이나 이런 걸 좀 하고 싶어서 수업을 듣게 되었습니다.
그러시군요. 오늘 제가 강의한 내용을 영어로 해서 좀 어색하긴 하지만 한번 학생 입장에서 한번 요약 한번 해줘 보실래요?
실은 이제 저희가 연구를 하다 보면 굉장히 좀 작은 스페시픽한 문제들에 좀 계속 바이어스 되면서 하기 힘들었는데, 데이터 센터나 AI, 그리고 실제로 산업계의 동향 같은 것들을 잘 설명해 주셔서 앞으로 이제 데이터 센터, 그리고 컴퓨팅 파워, AI, 그리고 컴퓨팅 파워가 계속 강조가 되고 있는데, 이런 과정 중에서 저희가 이제 집중을 해야 될 거는 5I 말씀해 주셨던 거, 그 5I에 집중을 하면서 이제 더욱더 트랜스미션 라인이나 아니면 그 컴퓨팅 관련된 부분을 메모리 그리고 컴퓨팅, 이렇게 3가지 모두 집중을 하면서 하면 될 것이라고 좀 큰 그림을 그릴 수 있게 있었습니다.
네, 아주 좋습니다. 아주 좋습니다. 제가 강의한 것보다 더 잘 설명해 주셨는데, 그래서 제 소신은 이렇습니다. 디지털 트랜스포메이션으로 세상이 벌어지고 있고, 그게 이제 주가에 반영되는 건데요. 거기서 가장 핵심적인 기술이 형식은 메타버스로 가고 뭐 얼굴은 바꾸지만, 자율주행 자동차로 바꾸지만 인공지능에 있다. 사람을 대신해서 이제 더 똑똑해지면 인간을 대신하는 거고요. 그러면 노동력도 줄고 비용도 줄고 그러는 겁니다. 그런데 그 인공지능을 학습을 하려니까 빅데이터가 필요한데 더 중요한 게 요즘은 데이터 자체를 인공지능이 만드니까, 컴퓨터가 만드니까 결국은 컴퓨팅 능력이 가장 중요하더라고요. 그래서 컴퓨터 능력을 좌우하니까 모든 회사들이 반도체를 직접 설계하는데 어찌 하다 보니까 메모리 없이 이게 안 되는 거예요. 네, 그렇습니다. 그래서 아까 폰 노이만 구조도 얘기했지만 메모리와 계산기가 얼마나 가까이 병렬화가 많이 되느냐가 성능과 전력 소모를 결정을 하는 거예요. 근데 그거가 보니까 트랜지스터는 더 이상 발전이 이제 멈춰지고 모의 법칙 때문에 인터커넥션이 다 결정하더라. 그럽니다. 근데 인터커넥션의 설계할 때 몇 가지 프린시플이 있는데 하나가 신호선이고 하나가 그라운드고 하나가 파워더라. 그래서 내가 시그널 인테그리티, 파워 인테그리티, 그라운드 인테그리티고 그 다음에 이제 그게 토탈리 문제로 나오는 게 이제 전자파로 형태로 나와서 오는 건데 디지털 시스템으로 보면 비트 에러가 생기니까 통신 퀄리티가 떨어지고 에러가 생기는 거고 학습이 안 되는 거고 EMI가 생기면 주변 회로나 센서에 영향을 미쳐서 신뢰성을 떨어뜨리는 거죠. 급발진이 일어날 수도 있고. 그래서 이제 제가 주장하는 거는 인터커넥션 문제를 풀기 위해서는 3디멘전으로 갈 수밖에 없다. 그게 이제 한 학기의 내용입니다. 근데 3D로 가자 보니까 이 열은 뭐 킬로와트, 메가와트까지는 아는데 3D로 가니까 쿨링 솔루션이 없어지니까 거기서 한번 또 한번 헤맬 것 같고요. 그래서 2.5D로 가다가 결국 3D로 가는데 저는 뭐 뉴로모픽 칩이니 뭐 여러 가지 솔루션이 있지만 현실적으로 패키징 레벨에서 하는 HBM 솔루션 그리고 Heterogeneous Computing 솔루션이 가장 솔루션이라고 보고요. 그렇습니다. 그래서 이번 학기에는 그런 관점에서 시그널 디자인과 파워 디자인, 그라운드, EMI를 어떻게 할 것이냐 그거 가지고 이제 강의를 계속해 나갈 예정입니다. I would like to spend about 10 more minutes to introduce overview of the class. So first part of the class is signal integrity. When we are designing our digital computing system, we are assuming zero level, clean zero level, and clean one level. Zero level could be 0 volt, and one level might be 1 volt. But this is ideal digital waveform. Actual waveform in the circuit or your computer may not have this form. And why is that this so difficult? Because we have higher I/O bandwidth. We are being asked to have higher speed because data bit is higher. Because of if your signal is becoming higher and higher, you're gonna have more parasitic effect. So because of parasitic effect, you're gonna have your interconnection will have more L or C type of parasitics, and then this waveform will be become very noisy. And also we're gonna have very large number of IOs, a kilo range or a number of mega millions range, then we're gonna have crosstalk issues. So even though logically we are assuming our digital signal is very clean, actually it will become very noisy. So our purpose of our class is how are we going to reduce these noises and how are we going to send digital signal as a speed of light. First, most important signal in your computer to consider signal integrity is clock data, because clock is the most fast signal and it will be delivered all part of your computing system and circuit. Second important part of interconnections to consider signal integrity is data. But data also has a little bit different shape compared to clock because data has more like random data patterns. It could be this digital waveform is more likely clock, but random data may have sometimes all 0 or sometimes 0, 1, 0, 1, sometimes 1, 1, 1, 1. depending on your different type of data, it may have different timing sequences. When you are dealing with random data, we usually use the eye diagram to measure how clean your digital data is and how noisy your data is. When we are considering signal integrities, we have different level of interconnection, on-chip interconnection, package interconnection, and PC level interconnections. If your signal frequency is going higher and higher, you will have more of inter-symbol interference issue. Usually this ISI issue occurs in communication systems, but if your interconnection channel is becoming lossy and lossy at higher frequencies, you're gonna have inter-symbol interference problem and crosstalk problem, deflection problems, and also you have to design terminations. And C-type termination doesn't work anymore. You have to make a 50 ohm terminations. If you use the 50 ohm terminations, you're gonna have huge amount of power consumption. More difficult part is that your power supply noise or ground noise will be transmitted to signal degradations, and that is called PSI. And sometimes you are going to use the single end type signaling. Sometimes you're going to use the differential line signaling. And to minimize the crosstalk, and if you want to maintain the 50 ohm impedance, we usually use the differential signaling. But anyway, one of the solution for all the signal integrity is the transmission line structures. And that is the subject of our class next week. And usually when we are characterizing the transmission line, we use the impedance, and usually we are going to use the 50 ohm line impedance. But this is the case of signal line. But when you are designing power line or ground line, we have to minimize the impedance below milliohm or something. 50 ohm is much easier. So that's why I said power integrity is more difficult. Once again, we have another challenges of power integrity. In power integrity issues, we usually have simultaneous switching noise problem. And because of our large, huge AI computing, current will be increasing and switching time is decreasing. So DIDT will be huge. I would say in the future, current could be 100 amperes or kiloamperes, and switching current DT could be less than nanosecond or picosecond. So DITT will be huge, 10 to 24 or something like that. Then how are you going to deal with the switching noise? You have to reduce the interconnection inductance. That is the huge, most important part of your power design in your computing system. So inductance, how are you going to reduce the inductance? You have to reduce the length of interconnection. Inductance is depending on proportional to the length of interconnection. That's why we have to use the three-dimensional structures. Second thing is that if you use more interconnection, it will effectively, inductance will be divided by number of interconnection. So you have to have millions of interconnection for power delivery. Single interconnection is not enough. That's how we can reduce this inductance. And another difficult part is the resonances. In your power delivery system, you're gonna have capacitance and inductance together. Usually we put decoupling capacitors and your interconnection has inductance. So it will create the resonances. Resonance means that you will have huge amount of impedance at certain frequencies. And if your data frequency are very close to these resonance frequencies, you're gonna have huge amount of simultaneous switching noise, and then it's gonna become an EMI source. And antenna efficiency will be huge because we usually use the planar or cable for power delivery. So we are going to talk about all these issues. And also very difficult part is that we have to reduce the impedance very low, near 0 ohm. It is really engineering limit. And when you are designing signal line, your target impedance is near 50 ohm, but in your case of a power line, it's gonna be near 0 ohm. So when you are sending your digital data 0 to 1, you are assuming very clean digital, but actually your power noise will be huge, and this will be transmitted to your signal, and this power supply switching noise will be becoming a source of your EMI. So this will be the major subject of our class in June and July. And also we have to think about the ground integrity, and ground is everywhere in your computing system and your circuit. For example, if you have automotive vehicles, your whole chassis of your body, of your car or trunk or your seat, everything become your ground. Actually, if you measure the voltage of your car, you can see the microvolt or millivolt range. And then your whole car system become on microwave oven, or maybe become an antenna for electromagnetic interferences. You assume that you have zero voltage for your ground, but actually when there is a switching of your digital devices, you're gonna see all this switching noise. And this become an antenna, and it will interfere with other circuits. So very, very difficult part of. And surprisingly, in your circuit diagram, half of your circuit is active circuit, and half of your circuit is actually return current ground. But there's no textbook in colleges, and there are very specific book in EMI society. We have a book on ground, but there's no textbook or chapter on ground. That is 사기. Why professors are not teaching about ground? Because they don't know about it. Because it is not written on a circuit diagram, and ground is not. It is purely the three-dimensional and is purely parasitic path. It cannot show up. Three-dimensional drawing cannot show up in your circuit diagram, and Kirchhoff voltage current law cannot be applied. That's why ground is most important, but hard to learn, but most important. The military area, it is also very important. Submarine or airplane, a car, they do not have ground. And our smart mobile phone, they do not have ground. And so this will be another important part of our class. And eventually, at the end of class, I'm gonna talk about electromagnetic interferences. Usually we have three sources: signal line, power line, and ground line. These are becoming an antenna. Why we do have more EMI problem in these days is because of our computing system, including automobile vehicles, we are using more current, we are dealing more high frequency data, because we want to improve the data bandwidth, GPU and memory. So that means we have to increase the clock frequencies. And also we have largest package PCB cable and chassis system. Who are suffering from this EMI? I would say Wi-Fi, LTE, 5G, 6G, AM, FM radios, who are very sensitive to small signal. And I would say sensors. Number one is RF system. Number two is sensors. Number three is the data system. Number four is computational system. Probably number five is it may be hazard to human brain and human body. And in metaverse system, we are supposed to wear the head mount display. Surprisingly, head mount display is a huge amount of EMI sources, because we have to do a lot of calculations there. So head mount display, that's why one of my former students are now working on these areas, and some companies of metaverse area are now working on this subject. This is a summary of overview of our class in this semester. 여러분, 제가 지난주, 이번 주 월요일도 그렇고 오늘도 그렇고 계속 이번 학기 전체를 설명드리려고 하고 있어요. 근데 왜 제가 이렇게 바로 수업에 안 들어가고 이렇게 이런 얘기를 많이 할까? 근데 제가 살아보니까 어떻게는 우리 학생들 잘 찾는 것 같아요. 저도 그렇고 누구나 엔지니어들이. 근데 why에 대한 질문을 하지 않고 하면 뭐 공부의 가치, 연구의 가치가 좀 줄어들지 않느냐. 자기만의 세상이 어떻게 변화하고 왜 그렇고 그러니까 내가 이거에 대한 확고한 생각이 있으면 논문을 쓸 때도 인트로덕션이 중요하지만 더 우리 학생들이 미래지향적이고 더 미래를 바라보면서 할 수 있지 않을까 이렇게 생각이 되고요. 만약에 수업을 얼굴 보고 하고 칠판에 하면 이런 얘기만 한 학기 내내 하고 싶기는 한데 그렇지 않아서 이렇게 갑니다. 다음 주부터는 또 강의를 계속 하겠지만 오늘 한 얘기가 다시 나오고 다시 나오고 합니다. 근데 또 강조하고 싶은 거는 이 인터커넥션, 그라운드, 파워, 시그널 디자인이 반도체 패키지뿐만 아니라 PC뿐만 아니라 자동차, 헤드 마운트 디스플레이, 핸드폰 다 적용되는 문제다. 공통적인 문제고 앞으로 미래의 시스템, 플랫폼은 다 믹스드된 기능을 가져요. 자동 주행 기능, AI 기능, 센서 기능, 통신 기능이 막 섞이기 때문에 이렇게 강력한 전류와 스피드를 쓰는 디지털 컴퓨팅도 있지만 바로 주변에 아주 미세한 시그널을 감지하는 센서도 있고 통신은 나노 마이크로와트 레벨에서 통신하는 거 아닙니까? 그러니까 서로 간섭할 수 있는 문제가 많은데 엔지니어의 실력은 남들 하는 거 비슷하게 만드는 게 아니라 더 성능 좋게 하고 신뢰성 있게 하는 거고 그럴수록 비싼 몸값을 받고 비싼 가격을 제품 가격을 받는 게 아니냐 이렇게 생각합니다. 그래서 우리 과목은 그 옛날에 그 미국에서 3M이라는 회사가 있는데 뭐 여러 가지 화학물질 만들고 테이프 만드는데 그 광고 이름이 I don't make product, I make the product better 이러더라고요. 저도 그렇게 생각을 해요. 저희 연구는 이 수업의 연구는 프로덕트 자체를 만들지는 않지만 프로덕트를 뭐 릴라이블하고 값지게 만들지 않느냐 이렇게 생각하고 또 한 입장에서는 책에서는 아이디얼 상황, 교육 목적에 맞게 그러면 수학으로 깔끔하게 풀리고 이러니까 그러는데 실제로는 그렇게 동작하지 않는다. 그리고 열심히 회로 시뮬레이션 해도 그렇게 안 동작하는 게 시그널 라인의 그 플라스틱 효과, 파워 더 나가서 파워 그라운드 아예 시뮬레이션 자체에 넣지 않기 때문에 그렇다 이런 말씀을 드립니다. 자, 여기 우리 학생들 한번 강의 한번 요약을 한번 들어볼까 하는데요. 얼굴 켜준 학생들이 그래서 우리 학생들이 많이 뒤로 더 가보겠습니다. 그러면 김혜연 학생이 한번 오늘 제 수업을 한번 요약해 줄래요? 김혜연 학생의 목소리로 이번 학기는 이런 거 가르치는 거다 한번 얘기를 해보시죠. 네.
네, 방금 교수님이 말씀해 주셨듯이 이제 저희 SIPI라는 분야 자체는 뭔가 프로덕트 자체를 만들기보다는 이미 있는 어떤 기존의 프로덕트에 좀 더 신뢰성을 높이는 그런 방법을 배우는 분야이고요. 오늘 교수님이 수업해 주셨듯이 시그널 라인이라든지 파워 디스트리뷰션 네트워크, 그라운드 리턴 패스 이 같은 것들은 저희가 회로를 공부할 때 사실 회로 시뮬레이션에 들어가지 않는 부분이지만 실제로 프로덕트 동작에 있어서는 굉장히 큰 영향을 끼치기 때문에 저희가 이제 저희 연구실 분들뿐만 아니라 다른 회로 하시는 분들이라든지 프로덕트 만드시는 분들이라든지 이 분야를 알고 계시는 게 이제 엔지니어로서 더 큰 몸값을 갖는 엔지니어가 될 수 있을 것 같습니다.
고맙습니다. 저보다 강의 잘하시네요. 그런데 이제 그 시그널, 파워, 그라운드라고 표현했는데 그걸 한 묶음으로 하면 그걸 저는 인터커넥션이라고 얘기를 하고요. 액티브 소자가 안 하지만 근데 인터커넥션이 컴퓨팅 퍼포먼스를 도미넌트하게 결정한다라는 게 제가 또 다른 이제 메시지예요. 그래서 양자 컴퓨팅의 세상을 확 바꿀 줄 알고 들어가 봤더니 거기는 인터커넥션 문제가 더 심하더라고요. 그래갖고 하여튼 그렇게 됐습니다. 인터커넥션. 그래서 이번 학기는 인터커넥션을 얘기를 할 텐데 알고 나면 세상일이라는 게 또 다 단순하긴 한데 여러분들하고 대화를 하면서 이렇게 공감해 가겠습니다. 일단은 제가 파워포인트도 수업을 하다가 제 막 연필로 쓰는 노트도 하다가 이렇게 말도 하고 막 섞어서 한번 해보겠습니다. 제가 강의 노트를 이렇게 지금 아이패드로 막 쓰기도 하는데 전에 또 슬라이드로 만든 강의 노트도 있어요. 그래서 합쳐서 여러분들한테 이렇게 제공하도록 하겠습니다. 오늘 몇 명 들어오셨나 한번 볼까요? 34명, 다 들어오셨네요. 여러분들이 바쁘면 이 강의 틀어놓고 딴 거 하셔도 되는데 그래도 살아보다 보면 이런 얘기를 듣다 보면 나중에 같은 문제를 볼 때 더 재밌게 볼 수도 있을 것 같고요. 아마 다음 주에 얘기를 하겠지만 여러분들한테 3월 중순까지 텀 프로젝트 제목하고 팀 구성을 받도록 하겠습니다. 네, 여러분 오늘 하루 좋은 하루 되시고요. 행복한 하루 되시고 건강하시고 또 그럼 다음 주 월요일 날 뵐게요. 다음 주 월요일은 시그널 얘기로 들어갈 텐데 시그널이 뭐가 중요한지 어떤 이슈가 있는지 또 한번 마음껏 떠들어보고 본격적으로 트랜스미션 라인 티어리는 아마 다음 주 수요일부터 또 들어가지 않겠나 이렇게 싶습니다. 네, 여러분 경청해 주셔서 감사합니다.
감사합니다, 교수님.
네.